Hi, this is Coach Dorf. Now we're going to look at a homework problem from Appendix E. The problem asks us to find this limit. Now, this looks complicated, and we may ask ourselves, why do we even want to do this? What's the importance of this problem? Well, it turns out that this limit is related to the definition of integrals. And we'll learn early on in chapter 5 that this limit is equal to the integral from 0 to 2 of the quantity x cubed plus 5x dx. And so we're going to use this idea as to help us better understand the definition of integrals. And then we'll learn later on in chapter 5 that we can evaluate this integral, that it will equal 1/4 x to the fourth plus 5 over 2 x squared, evaluated from 0 to 2. And when I do that, when I simplify that, I'm going to get 14 as an answer. So again, in the beginning of chapter 5, we'll learn the connection between this limit and the integral, because this becomes the definition of the integral. And then later on in chapter 5, we'll learn how to solve this integral, and we'll see that the answer is 14. So we should, when we finish this problem, get the answer of 14, although you wouldn't know that right now before doing this problem. Also, let me point out, the question might be, why are we even interested in the definition of integrals? And again, from a previous video that I showed, there are a couple of reasons why we're interested in the definition of integrals and definition of derivatives. One is not all functions can be integrated. And I give an example of one in that video. And second of all, if we understand the definition of the integrals, then we better understand how to solve certain problems. And I give the example of the case where there was a medical researcher who wrote a research paper and came up with this, what supposedly was this great idea on how to evaluate the area under this curve, and it was just the integral. And if they had known the integral, it would have saved them some time and it would have made the situation a lot easier. So that's why this problem comes up, and that's why we are looking at this problem. So how do I solve this problem? Well, the first step is we're going to need some formulas related to the summation. And so what are these formulas that we need? Well, if I have the sum I equals 1 to n of 1, that equals n. Next formula is the sum I equals 1 to n of I, and that equals n over n plus 1 all over 2. N times n plus 1 all over 2. Then fourth one is the sum I equals 1 to n of I squared, and that equals n times n plus 1 times 2n plus 1 all over 6. And the last one that we will use is the sum of I equals 1 to n of I cubed, and that equals n times n plus 1 all over 2, and that whole thing squared. So we'll need those formulas here. And those are in the lecture notes and also in the textbook. So how do we solve this problem? Well, there's some steps here. First step is I want to try to simplify the expression to the right of the summation sign. And I'm going to do that by trying to write it so we just separate the terms that have I in it from everything that doesn't have an I in it. So we're going to simplify the expression on the right-hand side of sigma. Again, we want to get the I terms by itself. And the reason we want to do that is that then we can use one of these formulas to help simplify it. All right, so what do we have? Well, to the right of the summation sign, we have the following: 2 over n, 2I to the n, in parentheses, cubed, plus 5 times 2I over n. All right, so simplifying this, I have 2 over n. If I cube the first parentheses, that's going to give me 8I cubed over n cubed plus 5 times 2I over n. And now I can write that as 2 over n times 8I cubed n cubed plus 10I over n. And then I can finally simplify that to be multiplying the 2n out front into everything. So I get 2n times that, I get 16I cubed over n to the fourth plus 20I over n squared. And I want to separate the i's, so I'm going to do one more step. I will write that as 16n to the fourth times I cubed plus 20 over n squared times I. And again, I want to separate those i's because then I can use the formulas. In the first set here, I have an I cubed, and that's formula D above. And the second one, I have I by itself, and that's going to be like formula B above. All right, so now what we need to do second is we're going to use the formulas above, and we're going to insert, well, I guess before we use the formulas above, we're going to insert the summation signs here so that we can then use the formulas. So now we're going to include the summation so we can use the formulas. So we start off, we have the summation I equals 1 to n of 2 over n times parentheses 2I over n, everything cubed, plus 5 times parentheses 2I over n. Now we're going to use our result from above here, and we're going to substitute that in here. I'm going to put that in right there. That didn't work out really well, but I think it's good enough to get the summation equals 1 to n of 16 over n to the 4th I cubed. Let me rewrite that. I rewrite that as I cubed that way, plus 20 over n squared. All right. Now, I want to again get it to look exactly like the formulas above. So I'm going to take out the terms that don't have i's in front of them. So I'm going to bring this one out, and then I'm going to bring this one out. Now, why can I do that? Well, in my summation sign, the variable, the thing that's changing is the I. So everything that doesn't have an I in it, I can bring out front. It doesn't affect the result, all right? And you may say, well, n's a variable. Well, it's an unknown, but it's not what's changing. What's changing is this part here in the summation, this I term. So that's what's important with the summation signs. So now I'm going to bring this up. Before I get to bring them out, I'm going to write this as two summations so that it'll make more sense when I bring it out. So I have 16 to the 4th times I cubed plus summation I equals 1 to n of 20 n squared times I. So now I'm going to bring out those terms again, as I showed earlier. I'm going to bring that out front and this out front. When I do that, I'm going to now have 16 n to the 4th summation I equals 1 to n I cubed plus 20 over n squared summation I equals 1 to n of I. Again, the reason I do that is now I have this and I have this. And these relate to, this is, I can use formula B from above. And for the purple one, I can use formula D from above. All right, so when I do that, now I have 16 n to the 4th. And what is that formula D from above? It says that when I have the summation, I equals 1 to n of I cubed, it's the same thing as n times n plus 1 all over 2, everything squared. And for the second one, I've got 20 n over 2. And then I have the green box there, which is the summation of I equals 1 to n of I. And using formula B from above, that is equal to n times n plus 1 all over 2. So then once I have those formulas, now I'm going to try to simplify these terms. And what's going to be important at this part is we're going to see that we're going to get a constant for each of these terms. We're going to get a constant times n to some power over n to some power. And in almost every case that we will do on these, when we look at the degree of n on the top and the degree of n on the bottom, they're going to be the same. And when I take that limit, that's all going to equal 1. So the constant out front is what's important. All right, so we're going to simplify these terms, and then we're going to take the limit. So what do I have? I have 16 on the top, and then I have an n squared, and then I have an n plus 1 squared. On the bottom, I have a 2, but that's squared, so that's a 4, and then I have n to the 4th. In the second term, I have on the top 20 n times n plus 1, and on the bottom, I have 2 n squared. All right, now notice, some of you can see this already. What's the degree on the top going to be on the first term? It's going to be n to the 4th. And on the bottom, I have n to the 4th. Now on the top, I have more than n to the 4th, but the degree, the highest power on n will be n to the 4th. And when I take that limit, which I'll do a little bit later, I know that n to the 4th on the top and the n to the 4th on the bottom, will take that limit will become 1. And I will just have 16 over 4 or 4 as in that limit. Likewise, the same thing for the second part. The second expression, I'll have n squared on the top and an n squared on the bottom. But to see that, we can just work this out. I have n squared times, now I do n plus 1 squared, that's n squared plus 2n plus 1 all over 4n to the fourth. And on the top, I have n squared plus n when I distribute that n through all over 2n squared. And so I can write this now as 4, and then I'll have on the top n to the fourth plus 2n cubed plus n squared all over n to the fourth. Plus, and then on the right-hand one, I'll have 10, and then I'll have an n squared plus n over an n squared. Now, the final thing I need to do is take the limit as n goes to infinity. Our original problem was limit as n goes to infinity of the sum I equals 1 to n of 2 over n times parentheses 2i over n cubed plus 5 times 2i over n. This was here. This was our original problem. And now we're going to substitute in what we have. So we're going to say this equals the limit as n goes to infinity of this quantity 4 n to the fourth plus 2n cubed plus n squared over n to the fourth. And by the way, where is this coming from? This part here, I'm using this, and I'm substituting it in here. So that's where I'm getting these terms from. And then I have 10 times n squared plus n over n squared. And now I'm going to break this up into two limits. So I'm going to have the limit as n goes to infinity. What can I do with this 4 out here? This 4, well, I can bring it out front because I'm taking the limit as n goes to infinity. 4 is a constant. It doesn't affect it. So I'm going to bring that 4 out front. So I actually have a 4 here times the limit of n to the fourth plus 2n cubed plus n squared over n to the fourth. And likewise, I can bring this 10 out front. And so I have the limit, 10 times the limit as n goes to infinity of n squared plus n over n squared. Now, what are those limits? Well, we talked about it in two different ways. Early on in the course, we talked about that if you had a rational expression like this, and we had it in terms of x's, but as x's go to, if the degree of the x's are the same and you take the limit as x goes to infinity, then that's going to equal 1 if the degree of this is the same, or it would equal the coefficient in front of the two terms. All right. Now, in this case, we don't have x's, but we have n's. But it's the principle still works the same. Another way you could think of this is L'Hopital's rule. Again, in L'Hopital's rule, we had x's instead of n's, but the idea applied in a similar way. And if I took L'Hopital's rule and I had x going to infinity, that limit, and I looked at these things here, it'll turn out that the limit in both of these cases would be 1. So in either case, this limit here is going to equal 1, and this limit is going to equal 1. And so I'm going to get 4 times 1 plus 10 times 1, and that equals 14. And that's my answer. Now again, let's go back to the very beginning where I talked about why are we doing this problem. Remember this problem here that we will see at the beginning of chapter 5 that this limit that we're doing here forms the definition of the integral. And when I write this in terms of an integral, it's going to equal this integral, this limit that we're given here. And then we'll learn later on in chapter 5 that this integral can be simplified or be evaluated to equal this amount here. Now you can see that this approach here in purple is much, much quicker than all we did down here to get the same answer. All right. But knowing the definition is important for the reasons I mentioned earlier, because some functions you cannot solve the integral for. And sometimes it's faster if you understand the definition of the integral than to try to reinvent this whole thing from scratch, like this one researcher did in the medical field. All right. Hope that helps.